Hi, this is Bert de Vries, and this is part 2 for the probability theory review. In part 1, we introduced probability theory. In particular, we introduced an interpretation of probabilities, namely the Bayesian interpretation, as a state of knowledge, as a belief. So when we write the probability for an event A, what we mean is what is your belief in that the event A is true. And that event can be anything. It doesn't have to be an event that is repeatable. You can have a belief about that it rains tomorrow, or the probability that there is life on Mars, and so forth. Any statement whose truth can be contemplated. We also introduced a calculus, namely probability theory, consisting of the sum and product rule that are displayed here. And these two rules basically make up how we update beliefs when new information becomes available. So what we're going to do in part 2 is just a few exercises and a bit of labeling here for relations between multiple events, some special cases. For instance, if I have two events, A and B, and we know that the truth value of B has no effect on the truth value of A, then they are independent. Technically, that means that the probability for A, given that B is true, is the same value as the probability for A. That also means that the product rule basically simplifies into the product of probability for A times the probability of B. There is another relationship between two events that is interesting, and this is called mutually exclusive. If two events cannot be true at the same time, they're called mutually exclusive. Technically, the joint distribution over A1 and A2 equals 0 if A1 and A2 are mutually exclusive. As a result of that, the sum rule simplifies to this. Normally, the sum rule here has a term minus the joint over A1 and A2, but this term goes away. So we have a special sum rule here, and for independent events, we have a special product rule. Now, there is a third property between a set of events that's interesting. That's called collective exhaustion. If I have a set of events, A1 through AN, and one of these statements or one of these events is necessarily true, that means that A1 or AB or A1 or A2 or A3 and so forth must be true, then basically I can write that the probability for A1 or A2 and so forth has to be 1, because the probability of true is 1. So these are special cases that that happens a lot, and so we give some labels to them: independency, mutually exclusive events, and collectively exhaustive events. In particular, if I have a set of events that are both mutually exclusive and collectively exhaustive, then something interesting happens. Then the sum of the probability of the individual events, well, I can write that as the sum of A1 or A2 and so forth, because this follows from this property that they are mutually exclusive. But this probability must be 1 because A1, A2 through AN are exhaustive. So this sum now is always 1, and that's interesting, because if I have if I involve other events, let's say events B or C and so forth, but for simplicity we have here a joint over a set of events AN, where AN, A1, A2, and so forth through capital N, they're all both mutually exclusive and collectively exhaustive, and we have a conjunction with B, then I can actually sum out AN. What's left over is just PB. In other words, now this whole variable A is gone from my equations, and it may sometimes be very useful. This is called marginalization, and this probability, the probability of B, is called the marginal probability of B. So this is basically a special sum rule. Some people, in some books, you will see this as a sum rule. It's a special case that follows, basically, if we have mutually exclusive events, the sum rule simplifies to this. If you take together with this collective exhaustive property, then we can integrate out basically all the terms that involve A. It's called marginalization. It's a special case of the sum rule. There is another rule, the product rule, which we can do something interesting. Now I'm going to talk about two variables here, d and theta, but it could be a and b or x and y. If I have a joint distribution, PD and theta, I can write the sum rule, of course, as PD given theta times p theta, or I can write it as p theta given d times the probability of d. And now all I do is I take the right hand side, these two factors, and I move PD to under here. So what it was, the result is, it's just a rewrite of the product rule. The probability for theta given d equals the probability for d given theta divided by probability for d times the probability for theta. This is called Bayes' rule. The reason why it is important is if you now assume that theta are, let's say, parameters in a model, and you want to learn the values for these parameters. And let's say that d happens to be new information in the form of data. I use d as because I'm talking about data. So observations in the world. Now what this formula says is that before I saw any data, my knowledge about proper values for theta was given by p theta, this one. Then after I've seen the data and I have incorporated the data in my beliefs, what I know about theta is given by p of theta given the d, given that basically the new information d. So what happens in between, multiplying by this factor here, that is basically the machine learning activity. This term on the right, which we call prior distribution, is what we know before we see any data. This term on the left, p of theta given d, which is what we call a posterior distribution, posterior meaning after having seen the data, is what we know after machine learning. And this equation basically is the machine learning equation. Apparently, if I want to go from, if I first have this knowledge, p theta, and I want to go through this knowledge, I have to multiply with this. And this is a function of both, basically, of the data, the probability for the data given the parameters, and the probability of the data. This is called Bayes' rule. It's always true, but it's very useful when we give when we talk about when one is a set of hypotheses or a set of parameters, and the other term, d in this case, is a set of data or new information in any way. And because this is used so much, there are we basically assign some labels to these terms in Bayes' rule. This is called the posterior, this is called the prior, this term is called the likelihood term, and this is the evidence term. But as you have seen, and this is really the fundamental thing, that Bayes' rule underlies basically learning from data. So that's why there is a term called Bayesian machine learning. Bayesian machine learning basically means that we're in the business of using this formula to do machine learning. And as you see, it follows straight from the product rule. There is nothing really strange about this, in the sense that you need nothing but just probability theory. So that's interesting, and of course we're going to talk about it a lot more in further lessons. What I'd like to do is maybe work out this example. Here's an example or a problem. It's a pretty famous problem. So there's a disease, yeah, D here, but didn't mean the same D as, of course, in the previously mentioned. There's a disease here with prevalence of 1%, which means that in general this disease occurs 1% of the cases. And there's a test procedure, 1% of the population. And there's a test procedure, and it has sensitivity of 95%. Basically, that means that given that somebody has the disease, in 95% of the cases, the test procedure will actually confirm that. It'll say, yes, this person has the disease. And this test procedure has a specificity, or a true negative rate, of 85%. And that's the chance that somebody does not have the disease, then in 85% of the cases, the test procedure actually confirms that. So the test procedure will come out negative. This person does not have the disease. So this is a good procedure. This is a good test procedure. 95% of the time that somebody has the disease, the test comes out, the test confirms it, and in 85% of the cases that somebody does not have the disease, the test procedure also confirms that. So, but I want to know now, what is the chance that somebody who tests positive actually has the disease? So if we translate this to probability theory, then we say the given data is the probability that somebody has the disease is 1%. 1% of the population has this disease. The probability that the test comes out positive if somebody has the disease is 95%. And the probability that the test comes out negative if somebody does not have the disease is 85%, or 0.85. So this is those are given. What I want to know, however, is the probability that somebody has the disease, given that the test comes out positive. And crucially, you should never confuse this term, the probability that somebody has the disease when the test comes out positive, with this term, the probability that the test comes out positive if you know that this person has the disease. These are two different things. What we can do, and this is an exercise you should just follow along with the product rule, we can write this. Let me just actually do this. So we want to know this, the probability that somebody has the disease given that the test comes out true. And I can use the product rule and say, okay, so that's the probability that somebody has the disease, comma, test is true, divided by probability that the test is true. That's just the product rule. The numerator I can rewrite as the probability that the test equals true given the disease is true times the probability the disease is true. That's also according to the product rule. P of dt t equals 1, I can write that as the probability that t equals 1 given, sorry, I'm gonna, yeah. This is really the probability t equals 1 comma d over all values, yeah, over all values for d, right? This is this is of course the product rule and the rule for the marginalization rule, and I can write this so as p t equals 1, d equals 1, p d equals 1, and just write this all the way out, p t equals 1, d equals 1, p d equals 1, plus pt equals 1, d equals 0 times pd equals 0. And now we just fill in the numbers, because this, I'm going back now to the lecture notes, because as you can see, this is the same what I have here. And these are all known, right? pt equals 1 given the disease was 0.95, pd d equals 1 was 0.01, and so forth. So I fill this in. What you get is basically 6% chance. So that is very different from this term here. The probability that the test comes out positive if I have the disease is 95%, but the probability if the test comes out positive, the probability that I have the disease if the test comes out positive is only 6%. So they're quite different, and all you've done here is just repeatedly apply either the product rule or the sum rule. And you can use marginalization to extend the conversation. Here in the denominator we had pt equals 1, but pt equals 1 is not given. So what we did is we went the reverse way of marginalization. We said, okay, then I'm going to write here p t equals 1 comma d and sum over all instances of d, and that's what gives you this. And now all these terms are given in basically the problem statement, so you can compute this. But crucially, with sum and product rules, we can basically compute all this stuff. Here's an interesting exercise. A bag contains one ball. It's known to be either white or black. Now I put in a white ball and I shake the bag, and I draw out a ball and it's white. So then the question is, what is now the chance of drawing a white ball? So the interesting part is that before I did this procedure, if I just have a bag with a ball in there and it's either white or black and I don't tell you anything, then what the chance of drawing a white ball is half, right? The interesting thing is you can compute if I do this procedure, I throw in a white ball and I shake and I pull out a white ball, and now I ask, okay, what is now the chance of that there's still a white ball in there? Then it is 2/3. And this is interesting because the color of the remaining ball is the same as the color of the original ball. Physically, it's the color did not change. If I had a bag with a black ball, then after this procedure, I still have a bag with a black ball. If I had a bag with a white ball, after this procedure, I still have a bag with a white ball. So the probabilities has changed from half to 2/3, when physically this bag is sort of still the same. And this shows you again that probabilities are about your state of knowledge about something that happens here in physical in nature. These probabilities are not a property of the bag or of the ball. They're a property of you, of your knowledge about what's going on here. If you would do this 1,000,000 times, if I have a bag and there's either a black ball or a white ball, and I throw in a white ball, I shake and I blindly pick out the ball and see it's white. And I do it again. I shake, it's white. And I do it again. I do this 1,000,000 times. So 1,000,000 times I throw in a white ball, I shake and I pick out a white ball. You will not believe anymore that the original ball in there was black. It has to be white, right? So your knowledge about what the color is of that remaining ball in the bag, that changes over time as you do these experiments. And this again speaks well to this interpretation of probabilities as a state of knowledge rather than a property of nature. The next exercise basically reinforces the same point. And you can read through that. I don't want to make the class or at least the video lecture too long. Basically, a little review. So the most important thing about this class is the interpretation as a degree of belief, a state of knowledge. It's not a property of nature. We can do everything in probability theory with the sum and product rule. In practice, Bayes rule and marginalization are very useful for computing the probability of whatever we want to know given whatever we do know. And that's really it. So I encourage you to read through the entire lecture notes. And if you have any questions, please write them down and let's discuss them in the Q&A section in class. Bye. See you then.